Welcome to the last in the FEKO webinar series for 2013. We'd like to encourage you to post questions for our presenter in the area provided on the side of your screen. These questions will be answered at the end of the session. For further information on FEKO, please visit our website or contact your local distributor. You're also most welcome to contact us via the email address that appears at the end of the presentation, webinars@feko.info. Berger from EMSS will now present the webinar Antenna Design and Analysis using FEKO, Antenna Magus and Optenni Lab. Over to you, Ernst.
Right, thank you, Fiona. I'm just switching over to my desktop. There we go. Everybody in the audience should now be able to see a slide that says Antenna Design with Antenna Magus, FEKO and Optenni Lab. Right. Welcome everybody. Let's start off this session. So our discussion today is going to be how can you design a custom antenna for whatever application it is that you are interested in using the combination of the tools of Antenna Magus, FEKO and Optenni Lab. So let me set you some context of how this talk is going to work today. I'm going to give you some brief background information on Antenna Magus, FEKO and Optenni Lab to set the scene. And then I will demonstrate the design flow by using these three tools as you would to do this in a more complex scenario. But more on the exact design and matching problem that we will be attempting this afternoon a little bit later. So let's start on the background information that I would like to present to you. And we'll start with Antenna Magus. Antenna Magus, if I have to present to you in a 20-second elevator pitch, is quite simply the first antenna design tool of its kind. Its huge searchable collection of antennas can be searched to find, design and export models of the design antennas to CST and to FEKO. So the features of Antenna Magus: quite simply, you can find or search for a particular antenna that would solve your problem or that would succeed in delivering on your requirements. You can design that antenna to your specification. Now, this is really one of the distinguishing points of Antenna Magus. It's not a library of pre-designed antennas that you have to use. You actually design any particular antenna to your specifications. Antenna Magus can also be used to estimate the performance of this design that you are doing in a custom sense, and it can then be used to export this model to FEKO, or as I mentioned previously, to CST as well, so that you can simulate this antenna on its own in a lot of detail, modify it, tune it, add it onto a structure maybe for antenna placement analysis, and so forth. So this is a typical representation of the antenna design process. You typically have to start by getting some system specifications that defines what this antenna needs to do. You then choose an antenna topology based on previous knowledge or experience, or perhaps some information that you got from a friend of yours. You might have to go and read a little bit about this information, so a literature study. You design a model and validate it in some way, and then you have to estimate the performance. Once you've estimated the performance, you might have to rework your design a bit. You might have to revalidate your design. You might even have to go as far back as choosing an entirely new topology because you figured out the first one doesn't actually do what you would like it to do. Once you've iterated through this loop, so all of the orange blocks in this little diagram, you could then eventually go to FEKO, where you would have to draw up this model yourself. So you'd use the primitives in FEKO to draw up an antenna. You could then simulate it. Once again, this is a little iterative loop. And once you're happy with this, you could build and measure a prototype and finalize the design. Now, this seems like a very cumbersome process. And this is exactly where Antenna Magus comes into the process to try and help you with this. So all of the blocks that are indicated in the orange is where Antenna Magus can do a stellar job for you. So the typical antenna design process no more. We're now going to replace all the orange blocks with Antenna Magus. So Antenna Magus is going to help you to select the appropriate antenna. You can compare a range of different antennas to select the one that does the best job for you. You can design it to your specification and export that model to FEKO in a ready-to-run state. This I will demonstrate to you a little bit later. Optenni Lab is a very good software tool for the synthesis of passive matching networks. It is a fast and easy to use matching circuit generation and antenna analysis tool that is tailored for antenna designers. Its main features include fast automatic circuit generation using a pre-existing component library, estimation of obtainable bandwidth of the antennas at various frequencies, and the calculation of worst-case isolation for two antenna systems that are communicating. Now, this is a lot of words to describe a process that is intuitively quite simple, as you will see later on. It is a very streamlined and easy process of going from a system that is not well matched in the impedance system that you want to a system that is really well matched in bands that are specified, once again, to your requirements. It will definitely become clearer as we continue to this section of the talk and the demonstration a little bit later. The FEKO and Optenni Lab design cycle looks something like the following. So once again, you'd have an antenna system. Maybe you've already used Antenna Magus. You've arrived at FEKO where you simulate this antenna system. You arrive at S parameters that describe the input impedance and the matching impedance match of this antenna. This impedance match or S parameters can then be imported into Optenni Lab, where you design a matching network of passive components, such as the one shown here, before you once again export this matching network in S parameter format to FEKO. In FEKO, this network is then imported as a non-radiating network, which matches your antenna using the network designed by Optenni Lab to eventually arrive at a system or an antenna that is well matched. I'll demonstrate this a little bit later. Background information on FEKO. For those of you who are not familiar with FEKO as of yet, what you're seeing now is what we refer to as the computational electromagnetics map. Now this represents all kinds of problems that any electromagnetics tool, not just FEKO, can claim to solve. Problems are easily categorized by the two axes that you can see on the screen. So on the vertical you have electrical size, and when I say electrical size I always think in terms of wavelength. How big is this problem in terms of wavelength that you are thinking of? Wavelength meaning multiples of wavelength, so thousands of wavelength if you think about the ship at the top left, or half a wavelength, 2 wavelengths maybe if you think about the little wire antenna at the bottom left-hand corner. Complexity of material is dielectric complexity. So think about something like a human head on the far right hand of the complexity of materials axis. A human head, when you do radiation hazard studies, contains many different dielectrics and is a very complex dielectric problem. As you move towards the less complex side of that axis, you have things like radomes, microstrip antennas in flat or curved surfaces, and so forth. What is now a key point to note is that FEKO has many different simulation methods that can be used to solve all of these problems. For instance, a method that is not yet available in FEKO is called the FDTD or time domain method that is available in various other codes at present. And as you can see, a characteristic of the FDTD is that it is very good at solving complex dielectric problems, but not so good at solving the electrically large problems. The same can be said for the FEM or finite element method, which is a frequency domain method and is also a method that measures the volume of the entire problem. In the same way as the FDTD, the finite element method is well suited at solving complex dielectric problems, but as you can see by the indicated boundary, it is not very good at solving electrically large problems. The next method to consider is then the method of moments. Now, whereas the finite difference time domain and finite element methods are based on the differential form of Maxwell's equation, the method of moments is based on the integral equation format of Maxwell's equation. In computational electromagnetics, that means that we only have to mesh the surface of the problem that we are solving, and as such we achieve a much more efficient mesh structure than you would for volumetric mesh solvers. The method of moment thus has a very good combination of solving larger electrical problems. As you can see, it starts again in electrical size, and also it can handle some dielectrics, but not as good as for the finite difference or finite element methods as indicated there. If you need to solve even larger problems, you can use something like the multi-level fast multipole method, which in essence solves the same integral equation mathematics as the method of moments, except that you use pre-existing knowledge that this is going to be a large problem, which means there are some fancy mathematical approximations and tools that you can use to solve the problem in a more optimal way than by the straight matrix-based solutions of the method of moments. These methods are all grouped together and can maybe called the full wave methods, which means they are physically rigorous solutions to Maxwell's equations. This is the best that you can do if you solve a problem. If you have even larger problems, you can start using methods like the physical optics or geometric optics, which is also known as ray launching geometric optics or shooting and bouncing rays in different softwares. And of course the UTD or uniform theory of diffractions. These methods are known as the asymptotic methods or high frequency approximations. These methods all have some way of assuming that the surface that it's operating on is electrically large, and that this makes it then simpler to do the approximate electromagnetic calculations for your simulation. The key thing to note from this graph is that no method can solve everything. There are boundaries where any method breaks down. Every method also has a strength, an area where it is particularly well suited at solving those problems. And the important thing to note is that FEKO hybridizes all of these methods, barring the FDTD at the present, and that these methods can thus be used at the same time in FEKO simulations. As the tagline said on the introductory slide, FEKO essentially combines the strength of these methods while avoiding weakness. Now, the simulation methods can be applied during antenna synthesis or simulation. As we will later, we will be using the method of moments, and all of the other methods can also be brought to bear on problems where this antenna is then eventually mounted on a car or a ship or an aircraft maybe. So, a wide range or a collection of simulation methods are available in FEKO with different strengths that can be applied to any problem depending on what it is that you are interested in. So let's move on to a demonstration of how these tools can work together in an antenna design space. So the flow that we will be looking at today is going to be to start in Antenna Magus, where we will specify our design and generate an antenna model. We will then simulate the same model in FEKO so that we can start to evaluate its performance in a rigorous full wave solver sense. And then we will proceed to Optenni Lab, where we will match this antenna to have good impedance performance for our intended use. The design flow that we're going to use today in a graphical sense, we'll set the requirement as indicated by the fuzzy cloud at the top left of this representation. As Magus says, we're going to explore for the design that antenna to our specification, and then deliver a model to the FEKO part of this tool chain. In FEKO, we are going to evaluate this design critically to see whether it succeeds in delivering on our requirements. And then we might want to use Optenni Lab to design a matching network to give us a better impedance performance of this antenna system. Eventually, we will then result in a custom designed solution to our specifications. The problem that I've chosen to work on this afternoon to demonstrate this tool chain is a simple directional booster antenna for a wireless LAN communication between neighboring buildings. So, for those of you not familiar with wireless LAN frequency bands, typical wireless LAN in this case operates between 2.4 and 2.5 gigahertz in various different channels that are spaced roughly from 2.4 to about 2.48 gigahertz. What I'm going to do today is to try and match this antenna that we are designing to better than minus 10 dB reflection coefficient for S11. I'm going to try and match it between 2.4 gigahertz and 2.5 gigahertz. So that means a center frequency of 2.45 gigahertz, which is a bandwidth of about 4%. We want this antenna to be matched to 50 ohm in our scheme of use. So right, let's start with this process. I already have Antenna Magus open in the background, so let me just switch to that. This is the interface to Antenna Magus that you are looking at the moment. When it starts up, you have on the main part of the screen all of the different antennas in the Antenna Magus catalog. If you scroll down, you will see there are a lot of antennas already covering a very wide range of different applications and different solutions to problems. Now, the chief benefit to Antenna Magus is what I like to call the Google function for antennas. And this is the search box. So if you are looking for particular antennas and you're not exactly sure which kind of antenna is going to give you the right performance, this is where you go. You can start by typing fuzzy signal is associated with the problem. So I'll type Wi-Fi, and you will see that Antenna Magus immediately starts to filter the terms based on terms that it already knows and can associate with antenna. I'm going to form the first word that we use to filter the Antenna Magus catalog. You have got 101 antennas that match the blue labeled keyword, which is Wi-Fi. Okay. The one up to the LAN, sorry, not LAN, we might want a wire antenna. Remember, we're going to build this thing ourselves. We need this to be simple. So let's add wire to this. And Antenna Magus will once again filter for us to now find the combination where both Wi-Fi and wire is matched. Now that's already significantly less. It's down to only 26 antennas in this case. And in this lot you can browse around and find an antenna that you think might suit your requirements. Quite a few around. Now, an experienced designer or somebody who is interested in doing this kind of thing might have had a nice chat with an antenna guru friend over coffee, and it's quite feasible that this friend would have mentioned a Yagi-Uda antenna, which is another keyword that I'm just going to add here, so we can just consider your friend's knowledge as well in this design. Now let's see what Antenna Magus can now deliver for us in this search requirement. So what you can see is that there is no match of both Wi-Fi, wire, and Yagi. At the top, once again, are all the elements that match Wi-Fi and wire. If we scroll down a little bit, we will get to the area where we have both wire antennas and Yagi-Uda antennas. And these are then the ones that are available to select to us. In this particular sense, this friend of ours we've now consulted was very sure of the fact that the Yagi-Uda antenna is the one to go for. So we might want to use Magus to first check whether this information makes sense before we delve into designing this particular antenna. So a very powerful feature to Antenna Magus is the info browser. So I'm going to click on the info button so we can review what is important about this antenna. Now you'll see in this info browser, I've already reviewed various other antennas in other work that I was doing at the top. But today we're going to look at the Yagi-Uda dipole array. In this case, Antenna Magus presents various information about the size of the antenna, so it's going to be a little bit larger than about half a wavelength. It's roughly got a unidirectional transmission pattern. Typical polarization is linear. Radiation pattern is broad uniaxial lobe. The gain, it's going to have a minimum gain of about 8 dB and a maximum of 21. Performance bandwidth, 10%, with a minimum of 5 and a maximum of 67. Remember, in this particular case, we're looking for a bandwidth of about 4%, so Antenna Magus this antenna will very easily give us the appropriate bandwidth. Impedance though is 25 ohms, so that might be a bit of an issue. It could be a minimum of 5, it might be a maximum of 50. We'll have to see. General, the beam width also looks within our specification we're prepared to accept, and the complexity is medium. Much more information is available, for instance, on the background of the antenna. If you have a look at the physical description, the antenna is usually constructed out of cylindrical aluminium tubes, sounds simple, and is supported by a central boom, once again, not so complex, with which the reflector and directors may make electrical contact. So if you're not the world's best handyman, this sounds like a fairly simple antenna to build, and it is something that we are now going to consider further. Much more information, including sort of the classical impedance you can expect for the antenna, radiation characteristics. There's a typical transmission pattern that you might expect for this antenna at its centered frequency, 2D radiation patterns on a polar trace, and also the normalized gain over frequency. Now in general, I think that this antenna is going to do a good job for the purpose that we have today, which is a Wi-Fi antenna for communication with a nearby building. So I'm going to trust my friend's advice and going to design this antenna. So I'm clicking on the design button, which takes us to the design mode of Antenna Magus. Now see once again the context changes. Now we've got various options. You've got sketches that automatically show you exactly what kind of elements you're going to be designing today and what this antenna will look like. To people who have not seen Antenna Magus before, there are also design guidelines which explains to you in very easy to follow terms how you can manipulate this design later on if you choose to do so by yourself. For instance, to increase the operating frequency, reduce the length of all the elements. Makes sense intuitively. What we're going to do now is we are going to select an appropriate design objective. So if I click on this drop down, you will see that we have various options that we can design for. I'm going to make this simple, and we're just going to design for the operating frequency. So if I select this, and we now have to pick our frequency of operation, let's start and say, what would this design look like at 2.4 gigahertz, which is the base frequency or the lowest frequency of the band that we are interested in. We click the design button, give it a little moment, and you will see that Antenna Magus has now generated a design for us consisting of 11 elements in the design. It's got all the necessary specifications to be able to build this design if we so wish. And below these specifications are the button where we can ask Antenna Magus to estimate the performance of this design. Let's have a look at what this design might look like. Now remember, in estimating design performance, Antenna Magus has various optimized formulae in the background that gives you a very fast estimation of what this antenna design can possibly perform like. You'll see that the design is finished by this little tab at the top, so we can head to the Estimated Performance tab and review the performance of this antenna. So you can immediately see there are various parameters that we can review. We can, for instance, review the impedance or matches of the antenna at the top. You scroll down a little bit, there is radiation patterns at the center frequency, which looks ballparkly acceptable to our particular use case. It's got a nice main lobe that drives in the direction that we want and not too much energy being wasted away from the main lobe. And it's got decent gain around the frequency, around the 2.4 gigahertz. Now the thing that we might already start to question here is that we've got some decent gain at 2.4, but it's almost flat-ish towards 2.5, but we're flirting with this boundary where there's a big roll-off in gain for this antenna over frequency. Let's have a look at the impedance bandwidth. So I'm going to maximize the view on impedance bandwidth so we can look at this in a little more detail. Now, every engineer has his own preference for evaluating designs. My preference is to review reflection coefficient. So we can see in this particular case that the reference impedance of 50 ohm, this antenna is not particularly well matched. At around 2.4 gigahertz, there's a little spot where it is matched better than minus 10 dB, but in general, it's not doing a very good job for us in a 50 ohm system. If we just switch back to the impedance graph for a moment, you can see that the peak real impedance is about 141 ohm, and the real impedance at the zero crossing frequency is about 14 ohm, with a mean real impedance of about 32 ohm, which kind of explains why we're having issues on the reflection coefficient graph. This antenna is not well matched in 50 ohm. The other consideration you can immediately see based on this simple and fast evaluation from Antenna Magus is the fact that it looks like this antenna is more likely to resonate between about 2.3 and 2.4 gigahertz than it is between the 2.4 and 2.5 that we are actually interested in. So, still in Antenna Magus, let's modify or create a new design and see if we can perhaps optimize our existing design to find a new antenna that is better suited to the frequency band that we are interested in. So I'm clicking on the new design button, and Antenna Magus is now going to generate a second design for me at, let's guess, 2.5 gigahertz and see what happens. We ask for a new design, which Antenna Magus promptly develops for us, once again with all the proper parameters to actually build it, and we can estimate performance. Once again, very fast, and now that that is done, we can compare in Antenna Magus the performance of these two antennas. Now immediately you will see that in the reflection coefficient, the new design, so design number 2, is much better suited to a possible good match between 2.4 and 2.5 gigahertz than our previous design was. So this design, pardon me, for 2.5 gigahertz is likely the one that we should proceed with in this case. So I'm just going to head back to the design tab, and let's then progress with this 2.5 gigahertz design to go forward towards FEKO to evaluate it critically before perhaps designing a matching network. So important, we have selected design number 2, and now we can use the last and very important feature of Antenna Magus, which is the export mode. Remember, search, design, deliver. Now in this case, we're going to deliver simulation models. You can obviously export a report, which is a very handy PowerPoint format, slides, that explains to exactly what this design is that you have now developed. It shows you various simulation parameters, the estimated performance, and so forth, and is very handy to keep next to you to perhaps review when you're building this thing or to report to somebody else. At present, we are just going to use the export mode to get a FEKO model. So we'll click on the export mode button and switch context to the export screen. You'll see it explains there will be various variables in the FEKO model. For instance, the center frequency will be denoted by a model name frequency underscore center and so forth. I'll refer back to those when we get to FEKO. We have various options for exporting. In our simulation today, I'm just going to use the simplest case, which is the thin wire model of the antenna that's fed using a wire port. I'm going to click on the button and ask it to export and open this model. I have a folder ready for this demonstration, and I will just call this model Yagi to start off with for simple access. So Antenna Magus is exporting, and you can see that FEKO is starting up in the CAD FEKO interface. Right, and there we have the model that was designed by Antenna Magus, that was set up now in FEKO, and that is in fact ready to run. Now let's just review this antenna for a moment. If we just rotate it slightly, you can see that this antenna does in fact have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements as per the design that Antenna Magus has done for us. All of the variables that Antenna Magus uses in showing us this antenna, for instance the length of the director elements, the different frequency specifications and so forth, are available in the variables column. The model is already set up. It has a port for exciting the model. There are even some parameters ready for optimization if we so wish to optimize this design. And then of course in the configuration tab of CAD FEKO, this is where we specify our solution requirements. You can see that this design has already been specified to request a 3D pattern. So we're going to review in a nice fuzzy way what this pattern is going to look like in 3 dimensions. The E-plane cut for this antenna, the H-plane cut, and of course just a single point over here at the end fire position of the antenna where we will measure the gain over frequency. Now let's just have a look at the frequency specification that Antenna Magus has set up for us in this case. You can see that Antenna Magus has specified this frequency requirement using variables. So it's going to have a linearly spaced frequency points starting at frequency minimum to frequency maximum, using the frequency num points variable as the number of points. Now I'm just going to review what these variables are, so let's go and look for frequency minimum to start with. Frequency minimum, you can see the variable in the CAD FEKO tree towards the left. Let's double click this and review. You'll see that is now 2 gigahertz. I'm going to modify this for the sake of time in our simulation this afternoon to a slightly narrower band. Now since we are interested in the band of 2.4 to 2.5 gigahertz, I'm going to give it just a little room to maneuver and ask FEKO to consider 2.3 gigahertz to be the minimum frequency for our simulation. In the same way, I'm going to cut this down to 2.6 gigahertz, which once again gives us what we're interested in. I'm also going to have a look at the number of points that we are simulating. So for, whoops, I've scrolled by, frequency point, which is not excessive, but for our purposes this afternoon, and ask FEKO to review once again. We are now in megahertz increments. It's going to simulate from 2 points, going to give us all the desired results that we have previously requested. So let's launch the FEKO item. Before we can do that is to mesh this model. Now remember, apart from these little changes that I've now made, I said previously that Antenna Magus exports ready-to-run models. Now this is also expands towards meshing. So if we go to the Mesh tab of FEKO and we invoke the Create Mesh dialog, you will see that Antenna Magus has already populated this dialog for us with custom variables that are well suited to the simulation of this particular antenna. I'm going to trust Antenna Magus and just ask this model to mesh. You will see that was a fairly simple process. We have 107 wire segments that we are going to simulate, so that's not excessive by any stretch of the imagination. I'm going to use these rapid action icons at the top to launch the FEKO solver so that we can get our first result to see what happens. Once again, there are some changes. I'll just allow FEKO to save them for us. And there we go, the FEKO solver launches. Now, the simple view of the FEKO solver that you can see running at the moment is our classic execution dialog that gives you an indication of how long it will take. Experienced users may elect to use the detail view that you can see at the moment popping up. If you're interested in reviewing exactly what is happening with the solution phases of a particular antenna, this is where, or simulation, this is where you would do it. In this particular case, the simulation is already completed, so there's not much to review. In case there were some problems or warnings during the simulation, these are all aggregated for you. For instance, in these tabs at the top, you will see that there were no errors or warnings. Hence, that was a good model setup by Antenna Magus. And of course, there are some notices that just indicate these are things you might want to take note of. You don't necessarily have to be concerned about them. If you want to, you can optimize your performance by taking note of these little elements. These are nothing to worry about, so I'll just OK, and let's now review the performance of this initial design by heading towards post-FEKO, once again using the quick launch buttons at the top right hand of the CAD-FEKO interface. So post-FEKO starts up for us, and it immediately loads a 3D view of the antenna that we have now just simulated. Now first things first, let's have a look at the 3D radiation pattern of this antenna so we can just get a rough idea of what this looks like. Using the drop down on the Home tab that is immediately available to us, I will ask for the 3D pattern to be displayed. You can see it immediately comes up. I'll just switch our display over to dB, and there we go. We see for the frequency 2.3 gigahertz, which is actually out of our band of interest, this is going to be our radiation pattern. Let's switch to something closer to our band of interest, so just inside the lower edge at 2.405 gigahertz. This is just about the radiation pattern that we saw in Antenna Magus we can expect for this antenna. So already we are getting good confidence that Antenna Magus has done a good job for us. Let's just review one more point to get more confidence. I'm switching it to 2.495 gigahertz, or just inside the upper band of interest. Once again, the pattern changes a little bit, but we are perfectly happy with this transmission. So now let's review the important impedance match that we are looking to optimize this afternoon. So I'm going to ask post-FEKO to draw for us a Cartesian graph by clicking on the appropriate button in the menus above. And now we are going to add a source data result to this trace. So clicking on source data, you can see that I am going to drop in the voltage source number 1, which is the only source in our model, so we can review the impedance of this antenna. By default, we're looking at the reflection coefficient in linear terms. So I'm just going to switch this to dB as well. And you will see that exactly as Antenna Magus has predicted, this antenna does reasonably well between 2.4 and 2.5 gigahertz, but not to the expected level that we are looking for, which is minus 10 dB. So we've got a very good potential solution here, but we still need to match the impedance of this antenna. So I'm going to leave post-FEKO for the moment and return back to CAD FEKO so that we can now start to optimize this design using Optenni Lab that is going to design a matching circuit for us. So first things first, let's save this model under a new name so that we can later compare the different results. I'll just use save as and call it again Yagi, except I'll just append match to the name and save. Now one of the key features of FEKO that is very, very handy is the scripting interface that we have. In previous releases of FEKO, we introduced the scripting interface first in post-FEKO, and also now in the latest release of FEKO, which is Suite 6.3, we have introduced the scripting interface and application macros in CAD FEKO. Now, the scripting interface is very, very powerful because it allows us to generate scripts or application macros, if you like, that can produce certain macro-like functions for us. In this particular case, you will see that if I click on the drop-down for application macro, there's already one for Optenni Lab port matching. Now this is something that our application engineers at the FEKO Development Center drew up for us, and that is distributed with FEKO. Now when I click on this button, FEKO will automatically launch a new simulation that develops the S-parameter block that Optenni Lab requires to do its matching job, and it will automatically then call Optenni Lab and instruct it that we are looking for a 50-ohm match before it allows us to specify what we want this match to achieve in Optenni Lab itself. So I'm going to click the button and let's see what happens. You'll see FEKO just saves itself again. It's created a new configuration for FEKO users. We'll notice that the existing one has just been commented out and we've run a new one. So Optenni Lab has started up, and you can see immediately Optenni Lab shows us the existing S-parameter block that we have imported. So this is the current performance of the antenna that we have now designed using Antenna Magus and that we have simulated with FEKO. On the right hand side you can also see a Smith chart representation. So once again, intuitively the trace doesn't really get close to the center of the chart, and we can understand that this is not very, very well matched. So let's proceed towards matching this antenna. Now, I'm not going to have an exhaustive discussion on Optenni Lab this afternoon. I invite you to review information on Optenni Lab on either the FEKO or the Optenni Lab websites. We are just going to focus on getting this antenna matched this afternoon to demonstrate to you the possible performance of Optenni Lab and the promise that it holds for you. So I'm going to do this by heading towards the Analyze tab at the top and designing a matching circuit using the Matching Circuit Generation tool. Clicking on that, we have a dialog that now starts to ask us some questions about what we want to achieve here. So firstly, we have to specify the frequency range that we are interested in. So clicking on the Add button, we have a new dialog that demonstrates to us what different frequency ranges we can design our matching network for. So if we use this drop-down, you will see there are a whole host and range of networks already predefined for us, so various frequency bands that people are generally interested in. Way towards the bottom, we already have one for the 2.4 GHz WLAN band, so I'm just going to click on this, which populates a dialog for us. However, in our case, we are interested in a slightly higher end frequency, so I'm just modifying this dialog to require a 2.5 GHz higher frequency match. And OK. Now you can see it starts to build a list. If you have a very complex network or an antenna that you might need to match in multiple bands, you can just carry on and add all of these bands as well. The next step that we need to progress to is the topology selection. Now in this case you can automatically create a topology, so this is the way I'm going to go this afternoon. We will just let Optenni Lab decide which combination of inductive and capacitive elements will form the best network for us. I'll return to this specification in a moment. We could use specific component libraries, but once again this afternoon I'm just going to leave Optenni Lab in its default state, which is to use generic capacitor and inductor models. We can specify various things, including losses for the various elements, limits, for instance, what kind of inductance and capacitance we will allow, resistances and so forth, tolerances on these elements, stop bands, and so forth. So I'm going to return to the topology now, and let's say we're going to consider initially we only want 2 elements in our design space. So I click OK, and Optenni Lab goes ahead and designs for us a circuit. You will see that it designed on the side. You can have a review the possible designs in the tree. There are a couple of designs, and it's already highlighting the best one for us, which in the band, as indicated by this solid blue line, is not exactly where we want it. We are not achieving the -10 dB level across our band of interest with this network that was already designed by Optenni Lab. So I'm going to go back to Analyze, Matching Circuit Generation once again, and we are just going to modify our topology to have more components in it. So let's double the number of components to 4 and then run the design again. And immediately you can see that the best design that Optenni Lab is now selecting for us achieves the goal that we have set it of a -10 dB input impedance match, reflection coefficient, across the entire band of interest. So we are happy. We have now found a matching network that we can use to match our antenna, and you can see what this network will look like in the circuit view window on the side. If I just undock that for a moment and expand this, you can very easily review the network. So you can see it's got an elegant collection of 2 inductors, 2 capacitors with the values included. It demonstrates where port 1 will be, which is going to be the excitation of our matching network, which is connected to the antenna, which would be load at port 1 in the simulation of FEKO that we're now going to run. So how do we now go back to FEKO? Very, very simple. By right-clicking on this dialog, we get a context-sensitive menu that allows us to do many things, but most importantly for today, at the bottom there is an option that says transfer circuit to FEKO and quit. So this is exactly what we're going to do now. I'll click on the button. You can save the work that you have done in Optenni Lab to review again later, but at the moment I'm just going to discard it and go back to FEKO. Right, so we're back to our existing FEKO model that we have previously named Yagi Match, and now we can review what has happened here. The important thing to note is now that in the tree on the left-hand side, when we review the configuration of this antenna, you see that we now have a non-radiating network that has been added to this model that was not there previously. If we enter a schematic view in CAD FEKO, you will see that this is now the schematics that we have in the model. There is the Optenni Lab matching network, there is the port of the antenna, and it's already been configured for us. You'll see that this script that we ran previously, the application macro as it's also called, has automatically imported the matching network from Optenni Lab as a non-radiating network. The output of this network has been connected to port 1, which is the port of the antenna that we are now going to excite, and port 1, which is the input of this non-radiating network, is open. If, however, I now review the configuration that we previously simulated, which is the standard configuration 1, and let's just have a look at this voltage source. Where is this now going? If you review the voltage source parameters for this simulation excitation, you can see in the drop-down where it says port that this voltage source has also automatically been modified for us to connect to port 1 of the new Optenni Lab designed matching network. So once again, this application macro that we now ran in FEKO launched FEKO to quantify exactly what the initial performance of the antenna was. It passed that to Optenni Lab, where we very simply designed a 4-element matching network for this particular design. We just said, thank you Optenni Lab, please return this to your FEKO for us. And once again, when we got back to FEKO, the script finished its job by importing that non-radiating network, connecting it to the antenna appropriately, and setting the appropriate excitation on the input port of the non-radiating network. So really, it can't be much simpler. We didn't do much, and we've got a fully matched antenna ready to simulate. Now, just reviewing the antenna again, it's exactly the same mesh we had previously. We've just added some electrical matching to it, so we don't even have to remesh again. I can just click the FEKO solver button and let the solver do its thing. So we'll just save the changes, and off goes the solver once again. I'll leave the solver screen in the advanced mode at the moment so that you can see how the solver is progressing both in total progress and in the current phase of any particular simulation stage. Now, as has happened previously, this is a pretty speedy process. It is finished already, and I can just click on the OK button. And now we can go back to post-FEKO, where we will review the performance of our newly matched antenna. So, first things first, we now have to add this model to our post-FEKO session. I'll click on the Add Model, and now I just select the ready simulated Yagi match model. And automatically, again, post-FEKO opens up our new antenna model for us in a 3D view. As we did previously, we can just briefly review the 3D pattern of this antenna. Once again, I will switch it to be in dB, and I will also change the frequency to, let's say, roughly in the middle of the band this time, 2.45 gigahertz, to review that the radiation pattern is once again roughly what we expected and hoped it would be for us. Now for the critical part, let us review the input impedance of this newly matched antenna. So once again, using the source data drop-down, we are going to add the impedance trace of the new antenna. You'll see I now have two different result sets that I can add. We already have the result set from the Yagi simulation. We're now going to add the result set from the Yagi match simulation. So click on that. Once again, it automatically arrives in the simulation in linear, and I will ask the post-FEKO to display for us in dB. Now immediately you can see that with this new matching network that we have added, we have in fact achieved a very good match for this antenna without altering the actual geometry of the antenna elements itself. I'll just modify the trace on the side so we can see easily where the minus 10 dB line is. So once again, FEKO context sensitive, I just right click on that tab and ask to modify the axis settings. In this dialog, I'm going to ask it to modify the vertical axis settings, deactivate the automatic grid, and ask post-FEKO to adhere to minus 20 dB as the minimum value for our trace and 0 as the maximum. And OK. As soon as that's set up, you can see very intuitively and easily that between 2.4 and 2.5 gigahertz, we definitely now adhere to our required minus 10 dB match. It's very easy to get some specifics on this particular trace that we are now measuring. you will notice that I've selected this trace in the traces dialog towards the right of the screen, and we can now automatically measure the performance of this antenna using the measure functions in the tree at the top in the ribbon. So I'm just going to ask FEKO to measure for us the reflection bandwidth to -10 dB, and immediately you can see that that is about 0.148 gigahertz, which is much more than we expected and is in fact very, very good. Let's just have one more analysis just to confirm that everything is as we expected to. Let's have a look at a Cartesian trace of the far field of this antenna, the matched one now. So let's look at the E-plane cut once again. We don't want to look at it via versus frequency. We're just going to switch this so that we in fact sweep the theta angle at the center frequency, which is 2.45 gigahertz. Ask FEKO to review it for us in dB, and we can see that using a Cartesian trace, this is roughly the performance that we would have expected. Once again, it's very easy to measure the performance of this antenna, which I'm going to do again. In this case, I'm just going to measure the half power with -3 dB beam width, which is about 33 degrees in this case, which is also very simple to review using FEKO. If you'd like to review this in a polar plot, it's also very simple. On the display tab at the top, we can just request to make a polar copy of this particular trace, and immediately, without having to set up the graph again, we get to review the performance of the E-plane cut of this antenna in the polar plot that you can see in front of you. So to conclude, it seems that we have a good radiation pattern going here. We have achieved the appropriate match for this antenna that we were looking for in the band that we were looking for between 2.4 and 2.5 gigahertz. So we can conclude that our exercise in designing a Wi-Fi antenna for communication between 2.4 and 2.5 gigahertz matched to 50 ohm to better than -10 dB reflection coefficient has been successful. So to conclude our session this afternoon, I just want to note again that I'm sure you will agree with me now that Antenna Magus, FEKO, Optenni Lab form a powerful tool chain for designers of custom antenna solutions. The combination of the three gives you the ability to check against a very wide range of antennas that you are getting the best possible antenna configuration for your design. You get to critically evaluate the design using FEKO and match it using Optenni Lab with a very, very simple chain of interfaces. This chain of interfaces complement each other well, and it has been demonstrated to you that they work very seamlessly with the different interfaces that have been set up between them. And last but not least, it definitely has been demonstrated that the combination of these tools makes for the easy design of custom antenna solutions. So even an inexperienced designer can come up with an antenna that has a matching network, that has dimensions allowing him to build this antenna to achieve a proper transmitting and receiving antenna configuration for whatever requirement it is they may have. That concludes the formal part of our webinar for this afternoon. More information on our webinar series can be obtained by emailing the organizers at webinars@emss.co.za, and at this time I will be happy to take some questions if you have any. Right, it seems that we are not receiving any questions at the moment. So once again, I invite you to send questions later on, if you think of them a bit later, to that email address, so webinars@emss.co.za, and I will respond to those questions as soon as possible and explain in more detail if you have more questions. So thank you from my side. That concludes the presentation for this afternoon, and thank you, Fiona. I return the communication to you.